To talk about why that's useful, and this is a query latency component I wanted to use as a core example. With traditional tools, you're usually figuring out what's happening on MySQL via the disk I/O level, such as by running IOStat. This is IOStat on Solaris, and it's got columns for reads and writes, kilobytes, and also the average service time. This looks pretty busy too. On this system, %busy is 99% for this 1 second, and the average service time was 9 milliseconds. So with %busy at 99%, this disk looks like it's flatlined. So if that MySQL database was having slow queries, and in this case it was, I'd probably be blaming the disks, just based on IOStat. However, this may not resemble the latency felt by MySQL, since that's measuring at the disk level, and there's a lot of kernel in between the disks and the application. You've got the entire file system in between. Not to mention that there are other applications using the disks as well, especially in cloud computing environments when you have other tenants on the same box. So even if this was a sign of pain, it might be a sign of pain for a backup application that's doing a nightly backup, not a sign of pain for your MySQL database. So file system I/O is not the same as disk I/O. Disk I/O, as seen from IOStat, can include unrelated I/O from other applications, like I just mentioned, and various things the file system does, such as prefetch or read ahead, which is not directly it's not directly blocking the application at that point. It's trying to be clever. And also file system dirty data flushing. For typically, an application will write to the file system, but it won't wait for those writes to complete to disk. File system will buffer it and then write it later. And even if at that later point those writes are really slow, it's not affecting the application. The application's off doing something else. So IOStat can be confusing to interpret. Disk I/O, as reported by IOStat, can also be inflated from the file system. So it can be rounded up to the file system record size. Your application could be doing 1 byte writes, but it has to round that up to 8K or 128K by the time it writes to disk. It can make it confusing to understand why the disk is doing so much work when you're doing so little work at the file system. You'll also get inflation from extra metadata for the on-disk format, the read, modify, write cycle of RAID 5. Both make it confusing. Disk I/O can also be deflated from the file system. So my application can be performing many reads that are satisfied from the DRAM cache of the file system, which you don't see at the disk level. And write buffering. So as I just mentioned, you can write to DRAM and you don't see those writes at the disk I/O level, but your application is doing them. And this one's particularly important. Disk I/O analysis can be blind to file system issues, such as lock contention in the file system. And I've seen many cases where there's some issue, which could even be a file system software bug, where there is milliseconds, hundreds of milliseconds waiting on a file system lock for that read or write to complete. This isn't at the disk level. So you're looking at the disks and you see nothing, but the application is blocked on the file system. File system queue latency. File systems do queue I/O. By the time they get to disk, you're not looking at the internal file system queue latency. There's also disk cache flush latency. Some file systems, such as ZFS, will send a SCSI disk flush cache command to ensure that the writes are on the disk platters and not buffered on the disks, on-disk DRAM. And the write I/O to the file system will only complete when that disk cache flush completes. According to IOStat at the disk level, it's only showing you the write, which is buffering it to the disk drive. It doesn't show you the full latency. So that's why disk I/O analysis can actually be blind to file system issues. We can solve this by tracing file system latency higher up in the operating system stack, such as in the application. This script, MySQLd PDFS latency, does it, and it's showing the latency for this MySQL database for reads and writes. This is the read latency, mostly between 2 and 16 microseconds, which sounds like it's hitting out of DRAM cache. Here's the write latency, mostly between 8 and 100 microseconds. Again, it's buffering into DRAM. There's just a tiny hump down here, which is the 4 to 16 millisecond range. These will be the disk hits, where it's actually waiting on disk. But most of the time, it's going into DRAM, so it's very fast. If there was a lock issue where you're waiting hundreds of milliseconds, you'd see it here in the distribution, since it's showing the time that MySQL spent waiting on the file system. This output that I'm looking at, I had it traced at the exact same time as the previous IOStat. And this is on a production system. The previous IOStat, remember, showed the 99% busy and 9 millisecond average service time, which looked alarming. But this production MySQL database is running at a 99.9% cache hit rate. It's flying. So whatever's happening up to the disks is not hurting this MySQL database. If I didn't have this tool, I may be chasing down disk I/O as a source of issues and wasting time before I figured it out. How it worked is it instruments functions OS file read and OS file write, and my read and my write. These are in MySQL and InnoDB. For those functions, it records a timestamp on entry, and then when they return, it just does the delta. So you know how long it spent doing that file system I/O. Again, a very simple script. The trick here was knowing which functions to trace. So once I found them, very easy to go and extract file system latency out of MySQL. If I run that on my production box, ooh. So I ran it for a few seconds. We can see that these writes, very fast, they're buffering into DRAM. Reads are also pretty fast. We have a couple of thousand that have gone to DRAM, but here are two outliers. So here is a read that took over 200 milliseconds and another that took over 500 milliseconds. From most tools, you wouldn't identify this. You wouldn't know about their existence. Again, they'll get rounded out from the average. But printing the full distribution lets me identify these outliers. And these could be contributing to slow queries if they're in the synchronous code path of a query. This could be a different asynchronous thread in MySQL that's doing file system I/O, where they're not directly affecting a query. This is interesting. This definitely points to file system latency as, even though it's very rare, it's only a small percentage, but it's something that I'd investigate a little bit further. Just run that again, and okay, now it's behaving a bit better. So here I had a few thousand fast. You can see this little hump here for the disk I/O for reads. So we're running probably with a 99% cache hit rate at the moment, and those are the disk ones. That script is tracing the storage engine I/O. You can use DTrace to trace any of these layers, and I could spend many hours talking about it. The MySQL query latency, like we did earlier, storage engine I/O, system calls, the kernel thread scheduler. You may actually have latency issues because the CPUs are pretty busy, and we have CPU dispatcher queue latency, and you need to be able to measure that from the kernel to know that you're being hurt by it. They'll get bundled up as part of the I/O latency. VFS, virtual file system, specific file system latency, block devices, SD for Solaris, SAS driver, even down to the PCI driver. Any of these can be a source of latency, such as queuing, software bugs, load, contention, locks, and with DTrace, if I had a serious latency issue, I can drill down until I pinpoint where that's originating from. Now that earlier, when I ran DTrace at the command line, I caught a couple of slow file system I/O. What I really would like to do is express that as a component of query latency. Not just that MySQL had experienced slow file system I/O, but what portion of a query latency was that? This script does that. This is MySQL d pid fs latency slow log.d. It's also on my blog. It was modeled after the slow query log, where it prints out line by line, and you can tune the threshold. So here I've tuned it to 100 milliseconds. It's printing out if the contribution of file system I/O is slower than that time. So if the file system I/O was more than 100 milliseconds and slowed that query, so now it is actually ensuring that this is a synchronous component of the query latency, it'll then print out a line. So for example, here we've got, this query was 500 milliseconds, 538 milliseconds. 509 milliseconds were due to the file system. Okay, file system's to blame. Well, maybe. I've also printed out the number of I/O. So there's 83 I/O for that query. So it's just doing a lot of file system I/O. This one here is much more interesting. It's a 153 millisecond query, which is entirely file system latency, and it was only one I/O. So that's one of these outliers. A single file system I/O is really slow for whatever reason. It could be a lock inside the file system, and that if that got very, very bad, it could be causing us slow queries. So important to have both the total query, the total file system latency, as well as the file system I/O count. And how that worked was it sets a variable, SelfQ Start, only during queries, so that when we're examining this file system latency, we predicate to ensure that this is during a query. And then we're able to sum up the total time spent waiting for file system I/O. Other components can be traced and examined in a similar fashion. I just wanted to show file system I/O. The previous scripts can be modified to include others from 22,000 available probes. And that is a lot of probes. There are ways to narrow down likely candidates, such as examining off CPU stacks. And that's how I found these. As a demo of that, this script is MySQL d pid off CPU.d. What it's doing is it's only looking at queries that are slower than 10 milliseconds, and it's printing out the rolling distribution plot. I just caught a slow query. I just saw it scroll off the screen. There's a few more. I'll Control-C, and what it now does is it was gathering this data in the background. This is the real report. This is showing the entire stack backtrace, both in userland and in the kernel, during the time spent off CPU. So this is when a thread blocks on a resource or a lock, and it goes off CPU, it saves a timestamp. When that thread comes back later, it can look at the delta time spent off CPU and can record the stack trace. One of the neat things about this is the stack trace doesn't change while you're off CPU, because you're off CPU. This stack trace tells us why we were blocked. In this case, it was for over 500 milliseconds. Walking up from the bottom to the top, we can see this is in server concurrent enter inodb, OS event wait, pthread con wait. So this is the inodb thread concurrency algorithm. It's causing the thread to wait. So this can be a sign of load. We have a lot of threads inside the inodb storage engine, and it's put these guys to sleep. And they've slept for a long time, over 500 milliseconds. So that's identified why they were slow. And if I go up, I can see other examples. In fact, I just wanted to mention this is, we can see dispatch command at the bottom of the stack. That's what I was tracing earlier for the query latency. Then it goes into MySQL parse, MySQL execute command, and so on. That was actually part of a MySQL update. There's another distribution. This one's for the same thing, server concurrent enter in a DB. Here I've got same thing. Same thing. This is not Percona, I should mention. This is an older version of MySQL that doesn't have that patch. This is a different one. This one has reached over a second. So this stack trace is during a slow query. And we've got server suspend MySQL thread and row MySQL handle errors. This is a very interesting code path that I've used DTrace to investigate further, because I can DTrace any of these functions individually. And what usually happens for row SQL MyHandle errors, at least when I've been looking at it, is it's handling database lock contention. So this is a DB lock wait event, and it's put that thread to sleep. And of course, I can get information out like the full query string, responsible, and other things that were happening. Let me just see if there's anything else interesting. I'm trying to see if there's any of these were based on file system I/O. And nope. So this is all. So we've got the DB lock wait related ones, and then the server concurrent enter in a DB ones, while I was tracing those off CPU stacks. If I had a significant file system I/O issue, you'd see the stack trace as it was doing the storage engine I/O, which is how I found the other functions. So this is a wonderful script. It's very general purpose. Any reason that MySQL leaves, a thread will leave CPU and then come back later during a query, I can record the entire stack trace and then look at the distribution of the time. The last thing I want to demo, and the last thing in this talk is about on-CPU latency. So off-CPU latency is great, but people are more exposed or maybe more familiar with the idea of profiling when an application is on CPU, what it's doing. DTrace can do that many, many different ways. Just as a quick example, and I don't even have a script for this, I'll just type it in. What I'm saying is use DTrace. DTrace doesn't just trace events, it can also sample events. I'm saying sample at 123 Hertz, frequency count the entire userland stack backtrace. So that was the one-liner I ran. On 60 occurrences, we were in do command, dispatch command, so we're doing a query, query cache, send result to client, and we're in times. It's actually getting timestamps, which is happening frequently, and that's actually on CPU doing CPU cycles. 54 times this was on CPU. We're in handle one connection, do command, my net read. So actually, this is likely doing memory cycles where it's moving data, reading from the network. And I can go through this and find out exactly if I have the type of queries that are on CPU, not off CPU, I can use profiling as a very simple way to find out what MySQL is doing. If I like, I can make these much, much more sophisticated, and I could DTrace individual functions and look at the V timestamp as they execute. Apart from performance and latency analysis, dynamic tracing can also be used for patch checking, which I wanted to mention. While I am using DTrace a lot for the cool performance things, patch checking is starting to prove itself useful as well. Last week I had a case where we didn't know whether a PHP patch was worth it, and we were able to use DTrace to confirm that a code path that the patch repaired was actually being taken. And so applying patches and then restarting applications or databases has costs downtime, and that's money for the customer. And so DTrace can actually be used to check that you're hitting that code path that's being patched, so whether the patch will be worth it. Just an interesting use of DTrace. Another one is troubleshooting, and if something is not working and traditional tools and logs aren't enough, you can use DTrace to follow the code, the arguments, the return values, times, more for the developer to understand why something's broken. So DTrace has other uses as well. Tools I used in this talk: PID provider scripts. I have many on my blog, dtrace.org/blog/Brendan. And there are some other ones from the DTrace book on dtracebook.com. The heat maps that I showed were from Joint's Cloud Analytics, which we're developing. And you can see there's a video of myself and Brian Cantrell talking about that. And we're intending to do the MySQL query latency. We do have the file system latency as a heat map already, but we're developing the others. For more information, dtrace.org, many DTrace blogs, my work blog, dtrace.org/blog/Brendan, and I've already mentioned these websites, and you can follow me on Twitter, Brendan Gregg. So I hope that was a useful demonstration. I was able to go into more detail without the time pressure here than I did in New York. The takeaway here is that dynamic tracing lets you examine anything. This isn't necessarily going to be the first tool you use for performance analysis on MySQL. There's many excellent commercial tools that do monitoring for you that can help you solve problems straight away. When you need to dig deeper, when you need to have arbitrary questions answered, when it's really worth it to go through the source code and to answer something with certainty, DTrace may be the right tool. Dynamic tracing lets you see all the functions. Use static tracing if it's available, such as USDT. It makes life easier. And what I've shown here is just really the beginning. Just looking at the file system latency as a component of query latency is one of hundreds of things I expect we'll be able to do in the future with MySQL as we discover more things. Thank you.